Hello, and welcome to CE 3305, and this is lesson number 4, and the general topic is fluid statics. So the next 3 meetings are generally on fluid statics. Let me briefly escape from the viewer document here, and we'll take a look at the syllabus. And so today we're roughly going to do pages 60 through 81 of chapter 4, I believe, and 60 through 81 for sources on submerged objects, and then finally buoyancy, stability, and manometry. So this is a lot to accomplish in the next 3 meetings, hence the videos. Okay, the chapter of interest is, chapter 3, and what we'll do in this video associated with this lesson is define hydrostatic equilibrium, learn about the difference between gauge and absolute pressures, discuss pressure units, define some of the aspects of hydrostatics, and possibly get into how pressure is measured. Okay, I believe this will be 3 or 4 videos plus whatever happens live in class. So let us return to what we have here and begin. Okay, so when we go back to mechanics, we had the concept of forces, and there are forces that are developed without contact, and they're distributed over the entire volume of an object, in this case a fluid element, if you will. And the example of that force is its weight. So the forces acted upon by gravity don't have to contact the object, although if you let the object go, it'll contact the surface of the earth for sure. There's other forces which are called surface forces, and these are forces that appear at points of contact. Probably the easiest surface force to visualize in the context of this discussion is, imagine you're standing next to a person and they're kind of in your way, and so you take your hand, you put it on their shoulder, and you press. You are applying a surface force. You have to contact the person. If you divide the area of your hand by the amount of force in newtons that you pressed upon them, you actually get a normal stress, which we're going to call pressure. So let's imagine a bubble. Bubbles are blue because that begins with the letter B. So there's a bubble. And we'll give it the artistic illusion of rounditude, although this will never get me invited to the International Street Art Festival. And let's look at just some area on the surface of that bubble. And I'll call that direction the X direction, this direction the Y direction. I'm implying by the curvature that they're somehow following the surface of the bubble. This entire area has magnitude dA, and in vector notation there'd be some outward pointing vector associated with it, the dA vector. That hand that we were pressing on it with earlier would be the dF vector, where F corresponds to a force. And if this bubble had some sort of tangential force applied to it, we'll call that the dF vector, and that's now going to be given the subscript tau to imply that that's a shear force, and this will give the subscript n to imply it's a normal force, and we'll eventually start calling it pressure. The third axis, which I didn't draw initially, is here. It's the z-axis. Which I didn't draw earlier is the z-axis. Okay, now, recall from our earlier discussions that stress is the limiting value of force over area. So stress, by definition, is some force divided by some area. And we're using dF, dA to indicate that we're looking at very small areas and differential changes in force. There's two kinds of stresses that are involved, at least from our drawing, and would be the case on the surface of any bubble of interest. There's a normal stress, and we call that dF of n over dA, and that has the same connotation as a pressure. So the normal stress in the case of fluids is the same as pressure. There's a shear stress, which in my drawing I show acting entirely along the x-axis, but that is not a necessary condition. It can act essentially anywhere in the plane defined by that dA unit. And in our case, it's dF of tau dA, and an example, this could be friction. Okay, so frictional forces divided by area are shear stresses. There's other forces divided by area that are shear stresses, but that's the quickest one I can think of. And the key thing is that a normal stress is perpendicular to the object, whereas a shear stress is tangential. Okay, so the usual notation is the symbol sigma for a normal stress and the symbol tau for a shear stress. And let me draw another sketch of that. So when it's applied in multiple dimensions, these will usually have double subscripts. It's a tensor notation. I think that's what it's called. So here's our z-axis again. Here's our x coming out to get you. And y-axis. And we'll just put a plane out here like that. And I'll go ahead and color it with red to remind us of our area of interest. So here's our normal stress, at least on that plane, and that would, in 3 dimensions, would be double subscripted, in this case with ZC. So what that is the force along the z-axis divided by the area from a stress along the z-axis. This shear stress here would be tau z, so it's the shear stress associated with the z-axis pointing outward from here, moving in the x direction. And this one would be tau z y. Then if this object became a cube, for instance, there'd be 3 times 1, 2, front face, back face, that's 3 times 2, and 4 is 6, it'd be 18 stress elements. Okay, so the normal stress by convention is into the plane, and the first subscript is the direction of the normal vector to the plane. The second subscript is the direction of the stress application. All right, returning to our thing here, by definition, sigma is going to be the limit as the area vanishes so that it goes down to a point of S sub n dA. That's normal. And tau is the limit as the area goes to 0. dF tau dA, and that's the shear stress, or tangential stress, if you will. And then, like I said, the double subscript. The first subscript is the direction of the normal vector to the plane. So let me draw that in blue. Okay, so direction of the normal vector to the plane. In this case, the plane is pointing in the plus z direction. So the first subscript of all three elements will be plus z. And then the second subscript is the direction that the stress is applied. In the case of this one, the stress is applied in the x direction, the stress is applied here in the y direction, and the stress is applied here in the minus z direction, but by convention, a normal stress is positive into the plane. So we just decide that ahead of time. Okay, because pressure, or normal stress in this case, is a normal force per unit area, at any point in the fluid we can discover that the pressure is going to be a scalar quantity. It won't have any sense of direction. So fluid pressure is the normal stress applied to a fluid element. Typical units of pressure are well, the force over area, so things like pounds per square inch in US customary, pounds per square foot in US customary, newtons per meter squared, which is a Pascal, in SI. Sometimes they're expressed as equivalent. Liquid column height, examples of that are inches of water, feet of water, inches of mercury, millimeters of mercury. And they're all equivalent expressions of pressure units. And then the last unit that's important is in atmospheres. Spelling there. And this is the ratio of the measured pressure to 1 atmosphere, usually at standard surface conditions. For instance, in the case of air at 59 degrees Fahrenheit, standard atmosphere is 14.75 pounds per square inch, 29.92 inches of mercury, 101.325, I think that's kilopascals, and so on. So there's lots of units of pressure. They're all three used quite a bit, and sometimes interchangeably. It's obviously problem contextual, but they're all conveying the same information. Okay, I'm going to break here, edit this video, and then